We're continuing with our conversation with the Department of Physics. And in fact, for generations of students at MIT, physics is always associated with the name of Professor Walter Lewin. He is one of MIT's lecturing treasures. And I do not say that lightly. He is a brilliant lecturer, as you'll see. And when people talk about physics at MIT, Walter Lewin's name comes first to mind. I'm very happy that he's here today to talk with you about some of his interests in physics, and the title of his presentation is How to Make Teaching Come Alive. And I think you'll see that in a very dramatic way this morning. Walter, welcome back again as another return visit with the science teachers at MIT. Thank you.
Thank you, Ron. So this is not going to be a talk about the frontiers of physics that you were exposed to this morning, but it is something about our daily experiences, about the world that we all know so well. And these experiences that we have, some of them can be quite wonderful, quite exciting. When you see a rainbow, when you see a sunset, I think we would all agree that that can be very beautiful. However, there is more to it. There's more to it than this beauty that all of us can see, and that is what I call the hidden beauty. It is the beauty of understanding, it is the beauty of knowledge. And it is our task, your task as teachers, and my task as a teacher, to get that beauty across. In fact, not only a task, it is your obligation. Now, we all love rainbows, and as scientists, we are so privileged that we can appreciate why the bows are there in the first place. We understand the color sequence, at least we should understand them. And we also understand why sometimes you see dark bands in the rainbow. And we understand why the bows are strongly polarized. And in fact, when I see a rainbow, I always take my own personal polarizer and I check to make sure that the bows are indeed polarized. Because it's almost as if I'm afraid that someday they may not be polarized anymore. And that physics won't work. And after today, now that you have your own linear polarizer, I expect you will do the same. So teaching has always been one of the greatest and most satisfying experiences in my life. And it is through the wonders of teaching that we can reveal the hidden beauty to our students. Knowledge does not narrow, knowledge only adds. And without knowledge, many experiences in life remain very narrow and very shallow, and that includes an appreciation for art. Now, today I want to talk about our daily experiences, at least some of them. And I will start with color. Ask the question, what are colors and when do we see colors? Now, these questions can probably best be answered by a philosopher, but I, as a physicist, will make a modest attempt. Imagine the sun is out, we have curtains, I make a hole through the curtains, and I let the sunlight in. And I take a prism, and with that prism, I decompose the sunlight in colors. Light is an electromagnetic phenomenon, electromagnetic waves, and we know that there are short wavelengths and there are long wavelengths. The long wavelengths, the red part of the spectrum, and the short wavelengths are the blue end of the spectrum. And so now you might think that the wavelengths of light exclusively determines its color. For instance, when I show you light with very short waves, you might think that you will see blue light, violet light. And when I show you light with very long wavelengths, you may think that you will see red light. And that is often the case, but not always. As a start, we all know that you can produce all the colors that you want to by mixing light. Mixing the light of the so-called three primary colors. We call that additive mixing, not to be confused with subtractive mixing, which is the mixing of paint. I'm talking about additive mixing, mixing of light. I can mix red light with green light, and I can make you see yellow light, even though the wavelength of yellow is not present. So this is the whole idea about color TV, which use 3 electron guns, and your computer monitors operate in that same way. Let's look a little closer at the three primary colors of additive mixing. And I'll show you a slide of what we call the color triangle. And this color triangle, in a way, is a recipe for how you can make these various colors using the three primary colors, red, green, and blue. So here you see, at the three corners of this triangle, you see red, green, and blue. Red here, green at the top, and you see blue at the other corner. And I will make here a poor man's version of the same triangle, very schematically. Oh, no, it should really be more of a triangle, like this. And so we have the green here, and we have the red here, and we have the blue here. Now suppose we want to make yellow, which you see here. So that's this point here. Then what you do, you put in this much red, away from the red from this point to the other corner, and you put in this much green, and then you will see yellow. If you make this color here, which would be some greenish blue, you draw three lines from the three corners. 1, 2, 3. And you put in this much red, and you put in this much green, and you put in this much blue. And you'll get that color. And so you see, we will even be able to make something that looks very close to white light by mixing the three primary colors the right ratio. And that's what is the basis behind your color TV. I have here a little box, and in that little box I have three light bulbs, red, green, and blue. And I can make an attempt to mix some colors for you. So here comes the red. Is that where it is? Yeah, that should be red. And I can change the intensity a little. And here's the blue, and here's the green, and I can change the intensity. Now suppose I make green and red. Oh, already it looks pretty yellow. It's a little bit a matter of taste, but you see I only have green and red, so I'm operating there on the right side here, and I'm seeing now yellow. I can also make purple for you. So this is now, we're now somewhere here, and I can also go to the purple side. So I only have blue and red. See, this is the blue. Oh, too many. I already am at the green. So this is the blue and the red. We mix that a little, and I can make it nice purple. And you guessed it already. You turn them all three on, and you change a little bit intensities, and you come close to white even. So now we are somewhere here. So I put a mixture in of these three colors. And so this is something that is boring, it's of no interest to you, and you didn't come here to learn about the color triangle. Now there's comes something that may surprise you, something that you may never have heard of, and something that is not covered in physics textbooks. And that is that you can actually see colors using only black and white, almost only black and white. And what I want to show you now is a very famous demonstration which was done in the early 50s by Edwin Land. The phenomenon was known before Edwin, but he really pushed the issue very hard. He gave me personally 2 slides. They're both black and white. You will see them very shortly. And they are slides of exactly the same scene. One of these slides he took through a red filter. So in front of the camera was a red filter. But gee, man, it's a black and white slide, so there's no red on the slide, of course. Both slides are black and white. And I'm going to show them to you. to do that, I have to walk back into the audience, and I'm going to make it very dark, and we're going to lower the screen, and we're going to look at these slides. Am I there already? Yes, close enough. Okay. So here comes slide number 1. Lifesavers and a clown. Tja. And I can show you slide number 2. So this is a black and white slide. This, by the way, is the slide that was taken through a red filter. But of course there is no red on the slide. It's a black and white slide. It's the other one. This was not taken through any filter. The same scene, taken from the same position. 2 black and white slides. You could ask yourself now the question, what happened if you hold a red filter in front of this one slide? I show you only one now. The one that was taken by Edwin Land through a red filter. What would you see if you put a red filter in front of it? Well, you'll see something very boring. You will see something that all children are familiar with, namely you look at the world through a red filter, and so you see all kinds of shades of red, pinkish, darkish, grayish. Nothing new. Exactly what you expect. What would happen if we project one slide exactly on top of the other, as accurately as we possibly can? And that takes about half an hour adjustment, which we did at 8 o'clock this morning, believe me. So the one is on top of the other. I'll show you. I'll take one out, and I will add it. Well, you see exactly what you expect, black and white. Now, I will put in front of one of the slides, the one that was taken through a red filter, I will put in front of that light beam a red filter. And now you better hold on to your chair, because I don't want you to fall off. Now you see colors. You see yellow, you see green, and I see some dark blue. And every time that I see this, this is absolutely mind-boggling. And I feel very sorry for the 10% of the males in my audience who are colorblind. But this is an incredible thing. So 2 black and white slides and 1 red filter. And you see colors. And none of this is ever covered in physics books. It's almost as if physicists want to ignore this because it certainly doesn't fit into the picture that we have in mind when we think of colors. We largely think of colors as connected to wavelength. There's a lot of work that has been done on this, a lot of publications, and there are actually nice algorithms nowadays which allow us to predict more or less the colors that you will see. But it is completely beyond the realm of physics. It's not up to physicists to explain this. So our hands are clean. This is something crazy that happens here, and that's where we don't operate here, right? Some people say, do the brains fool us? Is this perhaps an illusion? Well, that depends on your definition of an illusion. This is as real as you can have it, right? So I would think that this is not at all an illusion. You may say, yeah, I see all the colors, but listen, you did use a red filter, didn't you? No, I did use a red filter, yeah. I have here a demonstration which was developed in the late 19th century by Mr. Benham. Black and white. We will all agree, right? Black and white. No red filter this time. And when I rotate this about 7 to 10 times per second, you're going to see colors. Yeah, you have very special brains, but you're going to see colors. Look at this. Now, the colors are not spectacular. My goodness, what do you expect? How much did you pay for this lecture, right? But the inner circle is distinctly rusty brown, reddish brown, and the outer one, to me, looks dark blue, and then there is the second one from inside out looks a little grayish green, and then the third one out looks light gray to me. So there's something weird going on right here. What do you think will happen if I reverse the direction of rotation? You think you'll see the same colors or you'll see something else? You shake your head in this direction. What do you think you'll see? It changes the situation, right? Yeah, very good. You have an instinct for physics. I'll reverse the direction. Remember the sequence of the colors, will you? The rusty brown is on the inside and the dark blue on the outside. First have to stop the disc. Otherwise we ruin the motor. We don't want to do that. Hey. Hey. We see them reversed. Now you see this beautiful blue inside, almost cobalt blue. And you see the rusty brown outside. So, now you see colors only with black and white, right? And so if you want to explain that, again, as I said earlier, you don't want to be in physics because that's clearly outside our domain. And I think a satisfying neurophysiological explanation is not even available today, although there's quite a bit published on this in the literature. And I've tried to read up on it. And it comes down to a stimulation of the brains in a special way by flickering the light on the cells of your retina. And then the brains just tell you that you see color. Tja, what can we do about it as physicists? Nothing. Oh, yeah. If you go to speed too fast, then you won't see the colors. And if you go too slowly, then you don't see them very well either. It's optimum around 7 hertz. 5 to 10 hertz, either one is fine. So in the morning, we always play a little bit with it to get it right. But at 20 hertz, it fades away again. Now, when I lecture, I try to challenge my audience. And I always make them wonder, perhaps tease them a little bit. And at the same time, trying to teach them some physics. Students like that, and I see no reason why I should make an exception for you. I'm going to ask you 6 questions. 6 questions about rainbows, and I know that all of you have looked at rainbows, but looking at something is very different from seeing it. And I'm now going to test you to see whether you have ever seen rainbows. Now, you're lucky that I like you, because when I teach my freshmen about this, I ask them 15 questions about the rainbow. Only 6 for you. What is the radius of the rainbow? And some of you in the audience may say, radius? Well, how can you talk about the radius? Well, when you see a rainbow, then it looks like an arc in the sky, like so. Here may be the horizon. And since it is an arc, since it is a circle, there is somewhere a midpoint. That midpoint could be below the horizon, of course, say here. And so you have a distance here that you can express in terms of an angle. And that angle can be expressed in terms of so many degrees. Now, I don't expect you to know the exact answer. Is it 10 degrees? Is it 90 degrees? Is it 20 degrees? What is it approximately? So that's what I mean by angle. Radius in terms of angle. Color sequence. Is the red outside or is the red inside? Or does that depend maybe on the time of the day? Maybe the time of the year? Have you ever noticed that there is a huge difference in the brightness of the sky when you see a rainbow? The sky is much brighter in certain areas than it is in other areas. And I'm asking you, where is it very bright and where is it very dark? All relative to the rainbow. And then comes the question, is there more than one bow? Maybe there is a second one, maybe there is a third one. And if there is a second one, what is its color sequence? Is the red outside? Is the blue outside? And now comes question number 6. Are the bows polarized? And I already gave it away, didn't I? In my introduction, I said, we all know, or should know, that the bows are polarized. So you think you're going to get away with question number 6, but there's no such thing as a free lunch here. So I'm going to change this question into, why are the bows polarized? That's a harder question. Who knows the answer to all 6? Don't be modest. Dave, Raise your hand. Physics professor at MIT. Michael Caine, my personal physician. Michael, 0. Honest man. One of the few at MIT. Who knows the answer to 6 questions? Only David, 5. Marcos, you've seen this lecture 6 times. Who knows the answer to 5? Very good. Jeffrey Hoffman. You've only seen this lecture 3 times, right? So you forgot one. Which one do you not know? Why the bows are polarized?
I could guess, but
You're also modest. Who knows the answer to 4? Look, these are all science teachers. I'm going to make you feel as bad about yourself as I can. 3, who knows the answer to 3? Don't be too modest, because I'm not going to ask you what the answers are, so we will never know. 3, you know the answer to 3. 2. We're getting there. 1, who knows the answer to only 1 question. And who knows the answer to none? Come on, be honest. There we go. Nancy, nice that you're here. Okay. So, you've all looked at rainbows, but most of you have never seen them. And that's the way it goes. After this lecture, you will always remember the answers to these questions. You cannot forget, even if you try. Now, except for the last one, you can get the answers to the first 5 sort of by only knowing Snell's law. Sort of. So really high school physics. It's not quite true, you need a little bit more, but it's close enough. And Snell's law was discovered by a very famous Dutchman, Snellius, in the 17th century. It is the law of refraction. When light goes from air into water, the direction changes. And when it goes from water back to air, the direction changes again. We call that refraction. Now, to do justice to all these 6 questions will take a while. And so this is what I normally do during my freshman lectures, but since you are all science teachers, I don't want to bore you, so I will give you a poor man's version of the whole thing. So we go a little bit fast through it. But we will get the answers, I promise you. The first thing that you need to see a rainbow, you need water drops. It doesn't have to be rain. It could be water from a water hose, waterfall, spray from the beach, from the water, ocean. That's enough. And the rainbow will always appear away from the sun. So let's say the sun is there, rainbow will appear away from the sun. And another necessary condition is that the light from the sun must directly, unobscured, see the water drops. It is not necessary that you can see the sun. There could be a cloud between you and the sun, that's okay. But there cannot be any cloud between the sun and the water. If there is, then that water will not participate to the rainbow. So those are the only 2 necessary conditions. Water in the direction away from the sun, and the sunlight has to hit the water drops unobscured. Now, the water drops decompose the light in colors in a way which is somewhat similar to what a glass prism does. But now, I want to be more quantitative. And I'm going to make a picture here of 1 raindrop. 1 drop of water. It doesn't have to be rain. Okay, let me try to... Boy, this is a bad one. No problem, Marcos, I'll fix that. This is the only thing we didn't dry run this morning. Oh boy. Look what I did. This goes much better. Put it on my bill, will you? So here's the water drop. And let's assume it's spherical. It really isn't quite when it comes down. But let's assume it's spherical. It's very close to the truth. And let's assume for simplicity, for now, we're going to change that later, that the sun is there at the horizon. And so we get sunlight falling onto the raindrop from the left. Think of these as individual, very narrow beams of light. And they strike the raindrop, of course, everywhere. Light comes in like this. Also here and there. And since it is a sphere, you have to think of the whole thing as axial symmetric. So everything that you're going to see is axial symmetric around this axis. So you can rotate this axis around, and then you will get an idea of the three-dimensional picture. Let's look at this narrow beam of light. This narrow beam of light has an angle of incidence I, that's the way we define it in physics, as the angle between the normal to the surface and the incoming light. Some of that light will reflect, and some of that light will actually penetrate the raindrop. That is where the refraction comes in. That's where Snell's law comes in, and it will do this. So this change in direction is dictated by Snell's law. And this angle I will call R. And so Snell's law will tell you that sine I divided by sine R equals N. N is the index of refraction of water. I'm going to be extremely quantitative about that very shortly. But it's roughly 1.3. So you tell me what I is, I'll tell you what N is, and we can calculate R. When we reach this point, let's call this point A here. When we reach this point B of the water drop, some of that light will emerge into the air, for which, again, the angle follows from Snell's law. I'm not interested in that now. But some of it will be reflected. And, of course, this angle is also R. And then this angle is also R because it is a reflection. So the angle of incidence is the angle of reflection. And then we reach point C. And in point C, two things happen. Some of it is reflected inside the raindrop, and some of it comes out here. And that is what we want. This light enters at A, reflects at B, and comes out at C. And here is an angle which I will give the Greek letter phi. This angle, I will call that phi. So that's the angle that this light comes out relative to the horizontal line that I have here. High school geometry. Phi equals 4r minus 2I. If you close your eyes, you can almost see it. Not quite, but almost. There's 1r, there's 2r, there's 3r's, and there are 4r's here already. There's I here, and this angle also has to be I. And so, take my word for it. It's 4I minus 2I. 4r minus 2I. So that's this phi. So let's go through a very difficult exercise. Let's make I 0 degrees. That's this beam. Hits the water drop, and this angle between this line and the normal is 0 degrees. So for this one, I is 0 degrees. What is R? We go to Snell's law. And we ask Snell's law, what is R if I is 0 degrees? Doesn't matter what N is, R will have to be 0 degrees. Of course, the light hits the raindrop in the back and comes back straight. R is 0. So now we go to this difficult equation, and we say, what is phi? Well, phi is also 0. And so you've almost passed the course. I is 0, R is 0, and phi is 0. But now, since you're curious about these various incident narrow light bulbs, you're going to increase I in your mind 10 degrees. You calculate with this equation R. So you find a higher value for R. You stick it in this equation, and you find a value for phi, which is no longer 0. And phi will gradually go up, and up, and up. As you increase I, R will increase, and phi will increase. And now comes something quite remarkable. There comes a moment that phi reaches a maximum value, and I call that phi max. And if you increase I further, phi goes down. That's quite remarkable. In other words, this light that comes in comes back in this direction. And this light that comes in comes off a little bit like this. But then there comes a particular angle for I for which phi reaches a maximum angle and is never any larger than that. In fact, if you increase I, phi becomes smaller. And this now is at the heart of the rainbow, because this n is the index of refraction, which is different for different colors. The index of refraction for red light in water is roughly 1.331, but the index of refraction for blue light is a little higher. It's 1.343. There's a difference of speed of light of about 1% between these two wavelengths. You can now, through trial and error, which is an interesting exercise but a real waste of time, you can try to find for which value of I this phi reaches a maximum. And you can do that for trial and error. You punch in I in your little calculator, you calculate R using Snell's law, you stick it in this equation, you write down phi, and you slowly go up. And you will see by the time that I reaches 60 degrees roughly, that after that, phi will go down again. If you've ever done a little bit of calculus, then you can do much better. Because now you can take these two equations, you take the derivative of this one, you set d phi di equal to 0. And you can calculate now immediately for which value of I this ever happens. But that's very advanced physics, so I don't want to go into that. So we'll just make it down to earth. You go trial and error, stick in I, calculate R, calculate phi, increase I, and you will find then that for the two different colors, there are two different values for phi maximum. And the value for phi max that you will find using these numbers that I have is 42.4 degrees, and the value for I max for the blue light, for this index of refraction, is smaller, is 40.6 degrees, I believe. Depends, of course, on the index of refraction. And now, you should start seeing already some basic ingredients of the rainbow. Remember that whatever I've shown you here is axial-symmetric, so you can rotate the drawing around. So when the light comes in the top, this contributes to that crazy phi maximum, but when the light comes in at the bottom, it goes out at the top, of course, and it comes also at the sides. So what it comes down to is that if you have one water drop, and if light comes in like this, white light, and here's one water drop, that the light that will be thrown back is in a cone. And the cone has a maximum half angle of 42.4 degrees. That's the maximum value for phi, and that's only for the red light. Other colors cannot even do that. And so here I have a very special triangle. And if you can read, it says 42 degrees here, specially made for my freshmen, but I can use it for you today. So now, at 42 degrees, that is the largest angle possible. It's really 42.4, but we'll call it 42 degrees. The light in that cone can only be red, and the light in this cone here can also only be red. That's the maximum value for phi. Remember, this was that angle phi maximum. But for blue light, that angle is smaller. And so for blue light, it's more like this. Highly exaggerated, of course. And so what is going to happen is, light comes into the raindrop like this, a cone of light comes back through that journey, refraction, then reflection, and then refraction, and this cone of light here must be pure red on the outside. On the inside, it may not be pure blue, but inside this blue cone, all the colors can make it back, because if this angle is 32 degrees, or 30 degrees, or 20 degrees, the green light, the yellow light, the red light, the blue lights, all the colors can come back, and your brains will tell you, because your brains are very strange, that you see white light, all the colors superimposed on each other. And so each water drop, each little water drop in the sky, will throw back in the direction of the sun this cone. If you miss this, you might as well go home now, because then you will miss everything else that comes. This is at the heart of an understanding. The rest is not so difficult anymore. If I put a screen here, and I have a hole in the screen, I have a very bright sunlight coming in. We will do that later. And I catch on the screen this light that comes back, I will see the following. I will see red on the outside, and then I will see something that is bluish, but maybe not perfect blue, and then I will see inside here white light, and here I will see no light. Because phi cannot be larger than 42 degrees, and so no light will strike the board here. You see red, gradually the other colors come in, and then you will see white light. And that's at the heart of the understanding of the rainbow. Now, I'm going to put you out on the field. Here you are. And I'm going to make it rain. It's raining here. We don't want the sun anymore at the horizon, because that's too special a case. So we're going to put the sun a little higher on the sky. We put the sun there in the sky. Okay, you're standing there. Sun is there. What do you see? You see your shadow. And here is your head, the shadow. And here is your body. And here are your legs. That's just the way it is. That's what the shadow is, right? It just so happens that you'll be looking in this direction of the sky. You look at the rain there. There's a raindrop here, there's a raindrop here. Boy, there's thousands of raindrops in that direction. Each one of these raindrops is returning to the sun a cone of light. And that cone is red on the outside, and the rest we know. But I'm only going to draw you the red cone. And you look at this raindrop, and at this one, and this one, and this one, and this one. What will you see? What is the color of that raindrop? It's not red. You're not looking at this red light at all, because the red light is only on the outer part of the cone. So what color will you see? You see white light. Because you're looking somewhere here. You're seeing all the colors. You see it at a very small angle. So you see red, you see green, you see yellow, and so you see white light. Fine, keep that in mind. You see white light. That is the white light that is returned in the raindrop in the direction of the sun. Well, you're also looking in this direction. You're looking way higher up in the sky. And so here are raindrops. This is the direction of the sun. And so each one of those raindrops, they don't know any better, throw back at the sun, 42-degree angle, a cone of light. What is the color of that raindrop? Yeah? You don't see it. There is no light coming back. You're outside the cone. No light. So you're looking in a direction that is forbidden. Phi cannot be larger than 42 degrees. And if you would see light coming back, phi would be larger than 42 degrees. Boy, you're very good. Now, we're going to look in a very special direction. We're going to look in a very special direction. We're going to look into this direction. Raindrops. And this angle now, I have chosen to be 42 degrees. Notice it's 42 degrees away from the direction to the sun. Each one of those raindrops is going to throw back at me 42 degrees. This is the direction to the sun, and it's going to throw back a nice cone in the sky. What is the color of that raindrop? Red. Because I'm exactly looking at the right condition that I'm just seeing this part of the cone. So now you've almost created for yourself a rainbow. Because remember, it's completely axial symmetric, so you can rotate the whole thing about this axis. Because it's a sphere, right, the raindrop. So now what you're going to see at 42 degrees away in the sky, you're going to see only red. Every raindrop that is 42 degrees away from this line is only red. If you go inside, the bow will be white. Outside, there will be no light, and gradually, as you approach the white, it will become bluish. And so you're going to see something like this. Let's assume that the sun is alpha degrees above the horizon, so that this angle is 42 degrees. Then you will see the outside of the bow red, inside of the bow white light. And you may never have seen that, but it's extremely bright sometimes. It's really very bright white. Here it's dark. Dark means that you see the clouds. It means no light is coming back from the water, and the clouds normally are dark when it is raining, so that's why I say dark. You see the clouds, and then you will also see gradually the other colors come in, and so the inside then will have a blue appearance, and there you see the formation of the rainbow. Now, if you go through a similar sequence of geometry, in which you use Snell's law, and you should actually also use Fresnel's laws, which tell you about the intensities, it's a little bit more complicated, then you can also demonstrate that there is a second bow. We call it the secondary. This is called the primary. This is the brightest one of all. There's a secondary which is not at a 40-degree angle from the direction away from the sun, but it's higher in the sky. It's about 10 degrees higher. It's at 52 degrees, and the colors are reversed. And many of you may never have seen it, and the reason why you may not have seen it is that the primary is so much brighter than the secondary that you pay no attention to the secondary. But it's almost always there, provided, of course, that there are water drops at that 50-degree angle. I'd like now to look at a few slides first before we attempt to answer the questions. So let us look at slide number 1, which... Oh yeah, that's a picture that is very similar to what I just made on the blackboard, so that you can digest that again. You see here a person standing. This is the direction from the sun. Here's your shadow. Would be very long, your shadow, all the way up to this point. This is where your eye would be. And then you see this raindrop just at the right direction, 42 degrees away from this line. This raindrop will be red. And this raindrop begins to be white, maybe a little the bluish side, 42 degrees. I was not the first one to make this picture. Newton himself, who was the first to understand the rainbows. This is his own picture in the book Optica. You see here the primary bow. Notice the light comes in from the sun, penetrates the water drop, reflects in the back, and comes out. So this would be pure red. And this one could be red, but it can also be blue. It can be all colors, and here would be white light. And there's the secondary. The secondary allows for an extra reflection inside the raindrop. It makes two reflections. You see reflection 1, reflection 2. And that gives you the secondary, and the color sequence is reversed. Now you can make a rainbow that encircles your whole body. It's fun. It's great fun. I do that often when I sprinkle the garden. The sun is high in the sky, and you just put water all around you. It is a great feeling of power. And you see all the way around you this rainbow. Red on the outside, blue on the inside, and you see some white light scattered here. But you, of course, have to produce white. You have to produce raindrops everywhere here. That's to say water drops. If you don't have water drops, no rainbow. Oh yeah, this is a painting from the 8th century, Turkey. In the Bible it says, I do set my bow in the clouds. Now there's something wrong here with this picture. The color sequence isn't quite right. So there's two possibilities, three actually. Either physics was different in the 8th century, or the painter made a mistake, or the painter did this very purposely, so that we would always be puzzled. We will never know. It's a wonderful painting. If you can spare $12, then you can buy a rainbow. At least that's what this advertisement is telling you. And it says, why wait until after a shower to capture the colors in a rainbow? Now, I never see a rainbow when I take a shower, but that is perhaps my problem. But they say it's a rainbow maker for $12. But the colors are not quite right. Red is not on the outside, blue is not on the inside. It's a fake. But what else is new when you buy something? It's swindle, but it's nice. I'm sure you get colors. Let's now look slowly at the real thing. This is a rainbow that I made in the backyard when I lived in Winchester. And my daughter is spraying water from a garden hose. You see the water here. The sun is behind me. And you see all the features that we have discussed now. Red on the outside, blue on the inside. You see the white light that you may always have missed? And when you look here, of course, there is also water here, but no light comes back from these drops. This was not without problems. It was January. It was freezing cold. Poor Emma. But let's face it, you see the white light, you see the red on the outside, and you see on the blue on the inside. And this is not the only time that she suffered for the sake of science. And she still remembers it. It was January. I was going to give lectures at MIT 803, which is the physics of waves, and I really needed slides of the rainbow, so this is what you do then. The secondary cannot be seen. The secondary is very faint. But I did want to also make a secondary at home, and I succeeded doing that over my driveway, which is very dark. So here's a dark driveway, so the primary is easy to make with a garden hose, but you also see the secondary. 10 degrees further out, so the center of the rainbow is somewhere here, 42 degrees from here to here, and then you see the very faint secondary, red on the inside and blue on the outside. Oh, this picture was taken by Michael Sorgi. He sent that to me. He made it in, I think, in Austria. Again, you see the basic idea. The water is sprayed from a waterfall. Look at the white light. This inner light comes from this inner cone. Red on the outside, blue on the inside. And no light returns through a water drop. And now it's about time that you see a real rainbow, isn't it? There you go. Doug Johnson, the VLA in Socorro in New Mexico. Primary bow. Secondary bow. Look how dark the sky is here compared to here. Very light here. And then it is light here again. Well, if you do the ray tracing, you will see the same reason why it's bright here becomes bright there again. It's a great picture that has all the features of the rainbow that we discussed. And this is what you may have missed, this strong difference in light intensity. See a little bit of a dark band here? And that's the result. If the water drops are very fine, then you get a phenomenon which I didn't discuss, which is called diffraction. And this diffraction can cause dark bands. We call them supernumerary bows. The next bow actually shows it better. So this is a rainbow. You see again bright light, darker. And you see here in the rainbow, you see these dark bands. So they only occur when the water drops become quite small. So that diffraction begins to play a role, which what I talked to you about was only geometric optics so far. We didn't take wave phenomenon into account, but it plays a role when you get very fine water. In fact, when this water is extremely fine, then all these colors begin to wash out. You don't even see colors anymore. That's what you see here. This picture was taken by a student of mine, Carl Wales. It was 80 miles from the North Pole. This picture was taken at mid-June at 12 midnight, when the sun is always up there. And you see a rainbow here, a white rainbow. So there must be water drops there. This is not ice. Ice would not give you this arc. Ice is very different things. So there must be water here somehow. And you see these white, you see these supernumerary bows, you see the effect of diffraction. Okay, Tom, for now that's enough for the slides. So let's now return to the questions. And we have to get them up again. So if now I ask you, who knows the answer to the first 5 questions? Who knows the answer to the first 5 questions? The radius, color sequence, darkness, brightness of the sky. Is there a second bow? And what is the color sequence of the second bow? Let me phrase it differently. Who does not know the answer to the first 5 questions? Thank goodness. Not that I trust you, but okay. Now the 6th one, that's the hardest. We already discussed the fact that the bows are polarized. So that is a given, because I told you. Now the question is why? Does anyone know why? The answer lies in this picture, but in an indirect way. Be modest. Just say yes. Jeffrey knows. Good. Oh, good for you. When you reflect light, whether it is glass or air or water, when you reflect light off a surface, there is one angle at which the light in reflection becomes 100% polarized, and that's called the Brewster angle. And I can give you the relation how you can calculate that angle, but that's not so interesting. We all know, perhaps, that if you drive your car and you have puddles in front of you, and the light of the sun reflects off the puddle, not only is that irritating because of the reflection, but you also perhaps know that the light is largely polarized in this direction. That's why your sunglasses are polarized in this direction to kill that light. And that angle, in the transition, in going from water to air, that's what's happening here. You go from water to air, but you reflect off here. That angle, we call that the Brewster angle, can be calculated. Brewster angle, it follows immediately from n. If you know n, you can calculate it. For this reflection here is 37 degrees. It's a little bit different for red than for blue, but very close to 37 degrees. If you calculate what the angle here is, in the case that we see the rainbow, you will find that I is near 60 degrees, I mentioned that earlier, and R is roughly 40 degrees. That means you're only 3 degrees away from the Brewster angle. And that means that the light that comes in here that is unpolarized, that enters the raindrop, is still unpolarized. When it comes back at this point, it's almost 100% polarized, whereby the electric vector is oscillating perpendicular to the blackboard. So standing like this, it's polarized like this. But of course, since we're dealing with an arc, since the whole thing is axial symmetric, remember that, it's polarized here like so, and it's polarized here like so, and it's polarized here like so. And the reason is that it's the bouncing, the reflection in the back is very, very close to the Brewster angle. I like to walk on the beach, and Plum Island is one of my favorite beaches. And I have, at numerous occasions, looked at the waves coming in, water splashing up, these beautiful water drops, and then whoosh, for a split second you see a rainbow in this water. The sun is there, it's the location of Plum Island, you're looking always in the east, and then you watch again for another wave to come in. Wave comes in, water splashes up, whoosh, rainbow, and it's gone. And so I was there a few years ago with my friend Bill Pridorsky, also a physicist, and I thought, without insulting Bill, I want to point out to him that You look at the right moment, at the right direction, you see a rainbow. And so, there come the waves, water splashes up, rainbow. I said, Bill, look at it. He looks at it, sees nothing. And another one comes up, beautiful rainbow, gone. Bill sees nothing. So I got a little irritated with Bill because it looks all... Well, yeah, some people just don't want to see things, right? Even if it's obvious. And then I looked at Bill and I noticed he was wearing sunglasses. And the sunglasses that you buy in the store, this is the direction of polarization of your polarized sunglasses. And so, poor Bill was killing the light that came back. He was probably looking at this part of the rainbow, and his sunglasses polarized the light in this direction, so he wouldn't see them. So I said, Bill, do you ever not wear sunglasses? He says, yeah, occasionally. I said, take them off. He took them off, and he said, I see the rainbow. That's the proof that the rainbow is polarized. So now I want to demonstrate to you something that you may think is the rainbow, but it isn't. And since I don't want to mislead you, or students for that matter, I want you to appreciate what you're going to see. You're going to think you see a rainbow, but it's almost a rainbow, but not quite. I have one drop of water. Here it is, in a glass flask. And that is my one drop of water. And I'm going to shine an enormously bright beam of light right at you. Now that's going to be very unpleasant for you. It's like looking straight into the sun. But don't worry, we'll do something about that. So now you won't see it. You won't see the sun. So what comes back from that one raindrop, if I look at that one raindrop, this cone of light will come back in my direction. So there will be a red outside of the cone, gradually turning to blue, and inside white light. This white light. And I'm going to project that onto this screen. And that's what I'm going to show you. So it's not the rainbow, but it has everything in it that explains the rainbow. And that red light better be polarized, because that red light is the result of a bouncing of inside that water at very close to the Brewster angle. Now you may think that's why I handed out your polarizers. Wrong. Wrong physics again. Because once the light bounces off this screen, it's no longer polarized. It's only polarized where I am. I'm in a privileged position. For me, it's polarized. But what I can do and will do, I will hold a polarimeter in the beam so that you will see that I can actually show the direction of polarization. So we first have to lower the screen. And then your eyes have to adjust to the darkness. Don't put your hopes too high. You're not going to see brilliantly bright colors. I have only one water drop. Have mercy with me. One water drop. Don't put your hopes too high. So that's why your eyes have to adjust to the darkness first. So relax. Try to enjoy it. It'll take 30 seconds for your eyes to get a little bit used to the darkness, and then you will see the intersection of the screen with the cone of light, which is produced by that one water drop. And there you have it. Now I'm going to look for my polarizing. Okay. So let's agree that what you see, unmistakable, you'll see first of all that the red is on the outside and the blue is on the inside. And you also see white light here. And you understand now where that comes from. That again is reflected light in the back of the raindrop, but all the colors are superimposed on each other. And your stupid brains tell you that it's white light. They don't know any better. When we see all the colors superimposed on each other, our brains say that's white. But here, there is no blue. It's the surface of that outer cone, only red. And here, nothing. That is what we say, nothing. Of course, there should be a secondary here, but that is so faint that you can't see that. And so in here, the light should be polarized in this direction, and here it should be polarized in this direction, and I can show that with this polarimeter. So I have here a polarizing sheet, just the way you have it, except you can't use yours now. And you see here that I let the light through this polarizer. I'm going to rotate it, and now I've killed almost all the light. I think it's close to 98% polarized. And do the same here. Can let the light through. Now I rotate it, and you see I kill the light. So that means it's polarized in this direction. The direction of polarization of this sheet is like so. And here, polarized in this direction, kill it like this. So you're not looking at the rainbow, but you're looking at something that has all the ingredients in it that explain the rainbow. All right. Now, the next time that you see a rainbow, it will look very differently to you. I predict that you will check whether the red indeed is on the outside. It's a disease. And I can no longer cure that disease. And no doctor can. You will also try to find the secondary. And you will check that the color sequence of the secondary is different from the primary. And what you will probably do if you have your linear polarizer on you, which you should, you will probably want to check the polarization in the sky, which is quite remarkable. And all this joy and fun, you will get over and above the everlasting beauty of the bows, and you will see much more than people who do not have this knowledge and whose experience is therefore necessarily rather shallow. Your knowledge adds, it never, ever subtracts. Now, I want to change direction and finish this lecture with talking about sunsets and ask the question, why is the sky blue and why are sunsets red? The sky is blue for a very simple reason, that in our sky are very small dust particles and even concentrations, density fluctuations of the air molecules themselves, and the light can scatter off those fluctuations. It has nothing to do with the geometric optics. It's a scattering phenomenon. And if these particles are very small, I'm talking about a micron, a few microns at most, then the probability that light is scattered is inversely proportional to the wavelength of that light to the power 4. And in physics books, we call this Rayleigh scattering. Now, blue light has a much shorter wavelength than red light. And so if you take the ratio of the wavelengths of red and blue, raise that to the power 4, depending upon what you choose for the wavelength, you get about 7. So the blue light would scatter about 7 times more likely to scatter than the red light, anywhere from 5 to 10. So imagine now, you're here on the ground, and here's the atmosphere, and let's say the sun is in this direction. Sunlight comes in, hits the atmosphere everywhere in this direction, and you're standing here. Well, this light enters the atmosphere, and the only way it can come to you is through this scattering process. And so there is some light that comes to you. It's very likely that that's blue, because it has a 7 times higher probability to be blue than red. But not only will it be blue in this direction, but this light here is also scattered, also comes to you. And so the blue is highly favored over the other colors in the spectrum. And that is, in a nutshell, the reason why the sky is blue. It is essential, though, that the particles of which the scattering takes place is small, preferably 1 or 2 microns. If the particles become larger, say 10 microns, like the small water drops in clouds, then there is no preferred wavelength anymore. Or then it becomes independent of the wavelength lambda, and that's the reason why clouds are white. They are not blue. Because all the colors have roughly the same probability to be scattered. I'm going to tell you, before I do my demonstration to show you the blue color, I want to tell you something that I will not explain in any way, but some of you may know. But I want you to know the fact. If the light scatters over an angle of 90 degrees, which is approximately the case here, then that light that is scattered is also 100% polarized. Nothing to do with Brewster angle, totally different phenomenon. And the reason why I mention that, because now you can actually start testing your polarizers in the experiment that I am going to do. If it is not scattered over 90 degrees, it is partially polarized. A little bit, depends on the angle, but 90 degrees, strongly polarized. So that means when you walk outside after my lecture, and you look at the blue sky, let's assume it is blue, and you look 90 degrees away from the sun, which is a great circle in the sky, you can pick any point, and you look there, you will see by rotating your little polarimeter that that light is almost 100% polarized. So it's an extra bonus that I want you to have to appreciate the demonstration that is coming up. In astronomy, we see this blue light often from stars which don't have any dominance in blue light. Very bright stars, very hot stars, which produce white light, as white as we can think of it. Nevertheless, we can have the next slide. Here you see the Pleiades, and it's immediately obvious that you see blue light coming from the vicinity of those stars. There are these very fine dust particles, a few microns, and they scatter the light in your direction from those stars, and so the light becomes blue. It's the same reason why our sky is blue. And the next slide I find even more interesting. There's a man walking on the moon. Now, there's no atmosphere on the moon, so the sky would look completely dark in the absence of an atmosphere. But there is dust on the ground, and this astronaut is walking on the moon, and therefore some of the dust is thrown up and is surrounding the astronaut. And the light that you see, taken by the camera, is clearly scattered sunlight, scattered off these very fine dust particles, and is blue. Same reason why our sky is blue. So you see the Rayleigh scattering here, dependence of wavelengths, because that sunlight, of course, is as white as we can call it white. So now I want to demonstrate this to you by creating very fine dust particles, and those very fine dust particles will be dust particles in cigarette smoke. It's a demonstration that I don't like, because I have to smoke. The setup is all the way there. We have bright white light coming up, vertically up. There's a reason why we let it come straight up. And then here, I will put smoke of cigarettes. And whatever comes to you, no matter where you are, always comes out roughly at 90 degrees. That's why I get the double bonus for this thing. And in addition, if the particles are fine, but only if they're very small, a few microns, they will be blue. So the smoke will be blue, and since you have your linear polarizers, you should be able to see when you rotate it that the light is polarized. Anywhere in this plane at 90-degree angles, which is this whole horizontal plane, and all of you are in this horizontal plane more or less, doesn't matter whether you're sitting there or there, should see the light pretty much polarized. It'll be polarized, you're sitting here in this direction, polarized here, polarized here. And so I'll first try to create these very fine dust particles by simply having some smoke of cigarettes in that beam there. You see the light beam, and make it very dark when we get to it. And I have to now create some smoke, and that you do by smoking cigarettes, I'm afraid. Okay. So get your linear polarizers ready. Check, I'll have my polarizer here. Where's mine? There it is. But I can also have fun, not just you. So I will do nothing with the smoke, just hold these cigarettes in here. And many, not all particles are very fine, not all of them. Some of them are large enough that you see some whitish smoke. The blue stuff, I can see it bluish. If you refuse to see it blue, that's fine with me. And I can see a distinct difference in the light intensity by rotating my polarimeter. Now, if you don't think this is very blue, then I will try to convince you of that by making the particles artificially larger. I'm going to increase them to a size larger than 10 microns. And the best way I can do that is to hold the smoke in my lungs, because then there is moisture in my lungs, and you get water drops that will precipitate onto the small dust particles of the smoke. And then when I puff the smoke out, these particles will have grown then to 10 microns, and you will not see it blue anymore. It will be distinctly white. It may still be a little polarized, though. So, if you have the patience, then I will now put some of that stuff in my lungs, and then, just before I puff it out, I will still show you the cigarettes without having been smoke in my lungs, so you can compare the two colors. And by all means, use your polarimeters, huh? Was it white or not wide enough? I want it wider. That was white. So think about what you have seen now. You've seen that the Rayleigh scattering, the blue light. You've seen that it's polarized at 90-degree angles. And you also see that if you make the particles large, that you no longer see the blue light, but then it becomes white. And so now we come to the very large last part of my lecture, and that's asking the question, why are sunsets red? Well, sunsets are red because when the sun is low at the horizon, you're here, this is the atmosphere, and now the sunlight comes in almost like this. The sun is at the horizon, and so this sunlight has to penetrate an amazing amount of atmosphere. And this atmosphere has dust particles in it. And it has, as I mentioned earlier, it has density fluctuations in it. And so by the time that that light reaches you, there is no blue in that light anymore. It's all gone because of the Rayleigh scattering probability. But the green is gone. Everything is gone. The only light that can make it, perhaps, some of it is red. And so the light that reaches you has been completely exhausted of all its colors because of that 1 over lambda to the 4th relationship. And so what remains is red. And so if you look here at a nice cloud in the sky, here there's a cloud here. this cloud obviously will only see red light from the sun. So you look at the cloud and the cloud is red. And the filthier and the dirtier and the more air pollution, the more beautiful sunsets are, because you have more of these scatter particles in the atmosphere. Now imagine that it's raining at sunset. What would a rainbow look like? Now I'm really testing you, combining the beginning of the lecture with the end of the lecture. There is no blue light anymore. So the rainbow cannot be blue on the inside. Can the rainbow be white on the inner cone? No, but there is no white light. So all you can see now is a red arc, and this light inside the rainbow has to be red also. I've never seen one, but I have a picture of it. I have tried so many times. It got to rain just at the right time. It never does when I look. There you see one. Isn't that incredible? So you see only red, and then the light inside that arc is also red. It's supposed to be white, but there is no white light, and so it's red. Yeah, sooner or later, I will see this. So now comes the last demonstration, which will catch a few birds with one stone. I want to create for you, again, a blue sky, which I already did there with the smoke. And I want to create for you a red sunset by depriving the light, by sucking out of the light, the blue light, and only looking at the light that comes through after the blue has been taken out, the green has been taken out, and then the red is the only one that is left over. And the way that we are going to do this, Marcos is reeling it in, thank you, Marcos, is as follows. Ah, yeah, that helps if you plug it in. Thank you. There is here a small bucket with sodium thiosulfate. I don't even know what it is. I'm a physicist, so don't hold me responsible for that. But it's called sodium thiosulfate. And when you put a little bit of sulfuric acid in there, there's a chemical reaction. I see some of you shake. You must be the chemist in the audience. And you get sulfur precipitation. It starts with very fine sulfur, microns in size. We'll shine light through it like this. And so any light that you see, in the beginning, when the particles are fine, will be blue, because it's scattered of these fine dark particles of sulfur. For those of you who are lucky, who are sitting here, the light is scattered over 90 degrees. It should be polarized. You should get your polarimeters. For those of you who didn't pay as much, you didn't come early enough, partially polarized. So you can also use your polarization. It's not 100%. It's only at 90-degree angles. Remember, with the smoke demonstration, you were all at 90-degree angles relative to this beam. But relative to this beam, only a section of my audience is at 90 degrees. And you are not bad. 60 degrees, you will still see it polarized. So you're going to see blue light. You're going to see it polarized. And as the time goes on, these particles will grow in size. More particles will come. And the sky of this reflected light will become a little whitish. And you'll see what left over there on the screen has no blue anymore in it. And the green will go, turns reddish. That's what the sunsets are all about. So let me first put in this sulfuric acid to get it going. And then we have plenty of time. Make sure you get your linear polarizers. So I'm stirring it a little. And now I'm going to turn it on and make it completely dark. Okay. Now, here is your blue sky. It's already blue for me. And if you have your polarizers, and I have a polarizer here, so I can actually demonstrate it for all of you, this light here, if you understand the direction of polarization, should be vertically polarized. Unlike the smoke demonstration where it was horizontally polarized, but remember the direction of the light now is different. So I hold this in front of it here. For those of you who don't have your linear polarizer, and I'll rotate it. So now I have reduced the light intensity enormously, and now it lets it through. So it's polarized in this direction, the light. I will let you use your own linear polarizer, and you can try that. Rotate very slowly. And imagine you're out on the beach, and you're there with a friend. You can impress your friend now enormously. You can first of all tell your friend about the blue sky. You can even point out the polarization. And then you can also explain, perhaps walking pinky in pinky, that why the sun turns red. And you see the sun is really slowly turning red. The reason being that these sulfur particles are growing in number, and more of the blue light is scattered out of the beam. But not only will the blue light be scattered out, but of course also the green light is going to become victim. And all the colors will go, and whatever is left over will be strongly biased in the direction of the red. And we will give it a few more minutes, because clearly now that we are in this romantic mood, we really want to see the sun set, don't we? Pretty nice, isn't it? I would think that we can't be too far away from sunset. Oh boy, that's a beautiful sun. Yeah, indeed. Okay, enjoy your stay at MIT.
That word treasure loosely when I began. Walter, that was just absolutely wonderful.
You said the same thing 2 years ago.
I know. It still applies.